All right, then, yeah, it's my pleasure to introduce Monish for this presentation of the AGI. Professor Schultz is online from Spokane, so she asked me to do the introduction. But actually, most of you know Monish very well, since he was here for a long, long time until a couple of years ago, and doing his PhD here. And so now he's with PNNL. And actually, the last year of his PhD, he spent at PNNL because he was one of the PNNL fellows. So we're glad to see him back here. And he had no trouble finding parking. And so with that, I'll turn it over to you.
Sure.
Yeah.
Is my voice coming nicely to the folks who are online?
Yep, we can hear you.
Yes, we can hear you.
Awesome, perfect. So, hi everyone, I am Monish. As Dr. Bose introduced, I've been here doing my PhD and then been working for a couple of years at PNNL as a power systems research engineer. And most of my work is sort of in the areas of transactive energy, advanced distribution systems, distribution system planning and operation. So in today's talk, I'll mostly cover some basic concepts about transactive energy. We'll try to give you different flavors of how transactive energy can be used to coordinate DERs. And also some of our modeling and simulation capabilities that we have over at PNNL, we would like to share with you guys so that we can open up to those resources and then that make it more usable. So I'll have some background and motivation. What is transactive energy? Some coordination architectures, some mechanisms of how transactive energy can be used for different services, some modeling capabilities, and then summaries. So starting with a very basic background on power system economics, that we all know how conventional electricity markets are sort of hierarchical, and they have been top-down in their approach. That is, on the bulk level side are where generation resources get allocated, price gets determined, and optimal resource allocation and pricing are happening there, whereas it trickles down to customers, which sort of are the ratepayers, and they are basically consuming electricity and paying their tariffs. So this is a California ISO participant market. As you can see, that the orange are the active participants, and there has been planned EIM entries through 2021, 2022, and that's increasing. So this for California ISO, the number of participants are increasingly going up, which means that more resources and more operators are trying to get themselves in the market. And this is mainly also influencing how the electricity landscape is changing. With the proliferation of renewables, we all are aware of the duck curves that California ISOs are seeing. So as more and more of these operators started to participate in California ISO, you would see that with the increasing penetration of renewables, the belly of this duck sort of starts dipping, which means that during those middle hours of the day, as solar penetration is increasing, your load drastically decreases. And from the system level impact, once the solar sort of starts going down, the sun starts setting, you see there's a huge ramping requirement by generators, which means that the generators have to sort of stay in a non-operational but still connected to the system state, where you would have to bring the generators on quickly, ramp up their generation as the sun starts setting. From the physics side, this is the impact. There's also an impact on this on the market side of things. As you can see that these tremendous fluctuations of prices happening. You would see as the belly of the duck sort of groups, the prices also starts getting really low in the middle of the day. The prices start seeing negative prices. And this essentially means that a generator that's running, that generator has to pay to just get the generator spinning. And as you as a load, as a consumer, would just receive payments for consuming electricity. So this is becoming increasingly evident through different markets, not just California ISO, and that's why distribution utilities are thinking how they should operate. So from an operator's perspective, the distribution system is also changing. So previously it was just passive networks where customers were just ratepayers or end users, and now as more and more customers are sort of getting solar PVs and batteries, electric vehicles, and more controllable assets, the distribution operators are facing operational challenges with limited to no visibility or control over these devices that are connected behind the meter. From the business side, you would see the revenues are impacted. There's a reduction in the net utility sales. There's also a lot of variability and unpredictability because they don't know how these DERs are going to impact. They have very less visibility. So there is this figure. I found this really interesting. This basically shows the fluctuation of electricity price as compared to crypto. We think crypto is really volatile, and you would see that this is a 2021 figure of 2021 prices from PJM market, and these prices, electricity prices, are fluctuating even more than what blockchain prices crypto prices Bitcoin prices was varying. And this is indicative of how markets are becoming a little more unpredictable and how it's becoming inefficient. On the bottom, I have a stock price of some German utilities earlier in this decade. And you will see that the stock prices of some German utilities are also continuously decreasing, which sort of indicates that there needs to be a revision in the business models. Because Germany's and European countries were early adopters of renewables, so they saw this effect much before than what US utilities are seeing. So it's sort of a canary in a coal mine situations where utilities are trying to build up new models and trying to see how they can tap into these flexibilities. Customers, there is a huge, this change is sort of driven by customers where they are no longer consumers and are becoming more like prosumers, where there is an increasing awareness coupled with the decline in cost of these renewables that the customers have started to integrate them. There are favorable regulations of trying to get these solars with discounts from the government, and there has been an advancement of communication technologies and development of home energy management systems. So with this, the customers are more or less becoming prosumers where they can actively manage these underlying assets, which we call as distributed energy resources or DERs. And as customers are having these DERs, they're also trying to make use of these DERs. So they want more consumer-centric economies where they would be able to use some of these DERs to get incentivized for giving flexibility. With cloud-based platforms like distributed systems, with the oncoming of blockchain for decentralized transactions, these consumer-centric economies have started to gain a lot of traction. And through this traction sort of came up for quarter 22 in the year 2020, where FERC sort of passed on this regulation towards enabling DERs to participate in organized wholesale markets, sort of becoming level playing players with generators that are participating in organized wholesale markets. And through this, we are seeing initiatives like New York's RevVision, Brooklyn Microgrid, where these communities are sort of pooling their resources together, trying to organize themselves and get incentivized for it. So with this background, there's a little lag on the slides. With this background, how does transactive energy sort of come in? So transactive energy, let's understand some of the definitions. So the definition is basically a system of economic and control mechanisms that allows a dynamic balance of supply with value as a key operator. And what that means is that you can use transactive energy to control some of these resources, whereas the customers can sort of provide their flexibility and get incentivized for it. So a very typical demand supply curve is what I've shown over there. As you can see on the supply side, you'd see very cheap resources like wind, which are at the lower price, lower quantity section. As the price increases, you would see it goes from hydro to nuclear to thermal. And on the demand side, what it means that if the customers are able to replicate this demand responsiveness or this price responsiveness, what essentially happens is when the prices are really high, they would just keep some of their most essential end user loads on, which lights and refrigeration. When the prices are a little lower, you would probably turn on the water heater. When the prices are a little more lower, you would probably turn on your HVAC, and then essentially at low prices, you also charge your electric vehicles. So this responsiveness of customers with respect to increasing and decreasing price is sort of what we refer to as price responsiveness. And this is where transactive sort of comes in terms of enabling automation of such price responsiveness so that they could orchestrate operation of such DERs. It also presents market-based mechanisms for integrating DERs to participate in electricity markets. And then what we do is we sort of design agents which would house our on top of the DERs, and these agents are essentially coordinating this price responsiveness. So there has been a lot of demonstrations. PNL has been really active in the space of transactive energy. So for the past decade, there has been several field demonstrations and co-simulation frameworks that have been developed. What I will be showing through this presentation are different flavors of how transactive energy can be used for different coordination architectures, for different grid services, and essentially how we can take them from these pilot level implementations to evaluate true regional grid level flexibilities and grid level impacts. So we'll start with transactive energy towards different coordination architectures. And as we are seeing that customers are more or less trying to engage, I'm trying to present some coordination architectures where one would be a prosumer to grid, where the customer sort of tries to participate and coordinate with the grid. The second one are organized prosumer groups, where customers sort of pool their resources together to form communities. And these communities are basically trying to interact with each other and also have an operator in the loop to try to see how they can pool their resources and get the most economic use of their DERs. And then again, peer-to-peer, where you being a customer, you would try to transact your energy that you're locally generating to your neighbor and would try to do it in a more economically efficient way. So peer-to-peer becomes a little more futuristic. So what we'll cover over here are just some prosumer to grid coordination architectures and some community-based architectures. And you would see a timeline in the bottom. So in the timeline, what I'm trying to do is I'm trying to show you the work that I've been doing during my internship, during the PNNL WSU DGRP fellowship program, and also as a part of PNNL through my scientist and engineering career that I'm having at PNNL. So through this, you will also get the perspectives of how the projects were evolving, how I was learning the skill sets, and how that has helped me in my career towards the professional growth. So this is a hierarchy architecture of prosumer to grid. As you can see, the DERs, which is essentially solar PVs, batteries, your controllable thermostatic HVACs, water heaters that are on the lowest chain of the hierarchy. On top of that is the feeder level LSEs, which is sort of an aggregator. So they pool all these customer side resources. They would aggregate them at the LSE level. A couple of feeders join together to form the substation, which is the DSO level. And the DSO sort of participates in organized wholesale markets. That's the ISO level. And on the right, you would see the coordination mechanism. What we are trying to show over here is how the physics and how the market are sort of tied together very closely. So on the right side, you would see a customer would put bids. Those bids would get aggregated. Those feeder level demand would get aggregated to substation level demand, and they would get into the market. On the clearing side, the ISO would clear the quantity and price. They would send the allocation to a DSO. The allocation will trickle down to the feeder, and eventually price gets to customers. That's the market side. What happens on the physics side is residential loads sort of set their consumption. Based on that, the branch loads change, the substation loads change. They go up to the transmission level, which affects substation level voltages, again, distribution level voltages, and finally, making tap changers and capacitors act to regulate distribution level, customer level, service level voltages as well. So again, this is sort of that same coordination architecture where on the device level, a particular DER would bid their resources to the LSE. The LSE would take individual bids, aggregate them, send it out to DSO. DSO would aggregate them, send it out to ISO. And similarly, the process back where ISO sends clear quantity through to DSO, which is substation level, again, feeder level, and individual allocations to particular customers where they're responding to the prices. So basically how the architecture sort of works and how the values are flowing between different entities. Now, the question naturally comes at why do we want to do this huge simulation? Why can't we just model the distribution system? Why do we need to send these demand bids to the transmission side? So here is a very nice illustration which we found out of our simulations. Like if we don't model the impact of transmission system and just sort of limit ourselves to distribution system, what you would see is things would start becoming really unstable. So if we are only modeling price responsiveness in one way, where the price from the transmission system is just coming to the distribution system, and we are seeing the reaction of the customers or reaction of these transactive agents, you would see there is a tremendous amount of spikes that are happening. And this is mainly what in economic literature it's called as cobweb effect, where the price changes and it sort of swings back the customer demand. High demand again causes low price, and low price again causes high demand. And if we can represent the true responsiveness on the wholesale side, we have sort of seen that those cobweb effects go away. So at 25% penetration, you can see the impact of just prices to devices as well as the wholesale retail integration, which is the full T&D co-simulation. So with that preface, what we have done is we're sort of having an architecture. We have a price priority dispatch of flexible loads where we compute the prices on the ISO level, take those prices down to devices as we have explained, and then showed how does the devices respond. So on the co-simulation use case side, you sort of took the whole WEC system, the 240 WEC topology on the substation side, on the ISO side, and on each substation, we have been modeling distribution feeders. And what we have done is essentially allocate feeders with respect to their geographical location. So for example, we have got a feeder which should be located in Montana based on prototypical North American feeders, and also have imposed weather conditions of Montana similar to something in Arizona would get Arizona weather relatively hotter. So you would see this is the temperature distribution that is happening all over the system, where parts in the south are a little more hot, parts in the north are a little more cool. And once we have simulated this, what we found out is that we could essentially determine the flexibility on a geographical scale. So we would be able to find out what is the flexibility during summer for a bus at Montana and what is the flexibility of customers for a bus at Arizona. And for this simulation, what we have been using is just residential HVAC. So if all residential HVACs, a particular penetration of them would participate and express their flexibility, how much impact can we have on the ISO level? And essentially, you can see that we could get a 6 to 7 gigawatts of load flexibility during peak times at the whole California ISO level. So with this sort of large-scale simulations, we could identify ISO level impacts as well as flexibility at different geospatial locations. So now some of the key learnings and software skill sets that I've experienced out of this internship opportunity. So this was part of a CCSI initiative inside PNNL. Concepts that we learned are the cobweb effect of decoupled implementations, and as well that there is a spatial variation of that flexibility, and that's essentially important to take into account when we are evaluating the impact of transactive energy systems. Software skill sets are distribution system simulator, which is GridLab-D, which sort of facilitates end-user load modeling and also modeling these thermostatic devices like HVAC, electric water heater. Post-simulation tool we have used is Phoenix. On the wholesale market emulation, we used MatPower's OPF capability. And also, since we are doing simulation on such a large scale, also got some exposure to high-performance computing and had some opportunity to do some Slurm scripting. So, after that, I will move on to our next, which is community-based coordination and how transactive energy can sort of help us in community-based coordination. This is part of the work that I did when I was in PNNL as a part of the DGRP fellowship program. And you would see that the skill sets that I have learned are slowly getting built up on top of each other. So on this architecture, different from the prosumer to grid side, this is where a group of customers sort of pool their resources into a community. That's what you would see that. And then multiple communities are trying to sort of interact and transact energy among each other. The stakeholders are prosumers. They might have demand side DERs. They also might have supply side DERs. A community manager is sort of an entity which sort of gets a collection of this community of these DERs or of these customers, and then manages the energy consumption and manages the transaction that are happening between these communities. And then the DSO sort of comes in and also sets the electricity price and the surplus capacity to provide to the community so that everyone stays in service. So what we did is we sort of created a distributed architecture where essentially this group of communities would pool their resources together and do optimal dispatch. As you can see this with this graphic, what's happening is all the customers are sort of creating their price responsiveness. Those price responsiveness gets pulled up to the community level, and then based on that, they would just send that information, which is going to be prices, incremental prices and incremental quantities until they reach that this is our consensus price and consensus quantity for dispatch, and then they would dispatch. So we implemented this on both day-ahead and real-time retail level energy markets. For distributed optimization and co-simulation, we have been using Helix extensively. So Helix provides publication inputs through which we could connect and exchange information between GridLab-D and Python, on which we were coding up these community managers. Helix also has some endpoints through which you can do pseudo communication simulation. Essentially, you can create delays, you can create asynchronous communication when these informations are being iteratively exchanged. And they have filters through which you could control how you would want to model these delays. If you want to do uniform distribution of delays, or if you want to have certain packet drops on these endpoints. So some demonstration results, you would see we have implemented this on a 123 bus system. We had an all-to-all communication topology. And then on the top, I'm showing you market clearing prices. So the blue curve is what the DSO tariffs are imposed. So this is sort of a time of use price that the DSO imposes. And you would see that the communities would try to pool their resources together. And eventually at the time of the day where the prices are really high, That's where the communities would try to exchange and use their internal generation and not export any power from the DSO. Hence, they are driving their own price. They are becoming rate makers during these intervals. And the very figure on the top right, you would see are the net exports that are coming out of the DSO. So you would see at the point of the common coupling, it's almost zero during those peak hours of the day, which means it's not buying any power from the operator. It's just trying to use its resources internally and operate at its own prices. Since this is a distributed architecture, as the communities are exchanging information iteratively, we also try to see the impacts of communication. So the animation is showing basically the top one where you have asynchronous communication. If this asynchronicity increases, you would see that the LMPs or the prices would not converge, essentially giving rise to very erroneous dispatches, as you can see on the right side on those dashed black lines. And if you can take into account those delays and ensure synchronicity in the data exchange, what we can do is essentially get rid of those erroneous dispatch and can make them dispatch accordingly.
Hey, Monish.
Yes.
I have a question. Actually, how you are breaking these subsystems, so you are showing few different colors, but this part of the network is intact. So
yes, so
it's not distributed.
So essentially what we are assuming is the communities are located all on the colored portions and everything else is sort of DSO operated.
Okay, so then how you are dividing, like they are same community means what? Like nature of load is similar.
Yeah, so they would have a mix of residential customers. They would have a mix of PVs. They can also have backup diesel generators. So you would see some of them are really small. So these are just one load, one diesel generator units. And essentially what they want to do is that they have a backup diesel generator. Why don't we use it to sort of get some energy arbitraging or get some more benefits out of it?
So this part of the network is then still centralized.
This part of the network is operated by the DSO. This part of the network doesn't get affected. Only some communities have decided to pool their resources together. The other ones are not part of the community.
So they can also get back to the substation then,
yes,
if they want.
Yes. Yes.
So then it is distributed architecture. I am just
yes.
Okay.
So we are distributing basically on the community sides. So on the couple of communities that you are seeing, they don't know what is happening on the price. So they are just trying to exchange some price signals and quantity signals and try to decide how they would independently pool their resources together.
Okay. So that boundary can also change, right?
Yes, absolutely.
Oh, so it's very random then.
Yes, and this is a very particular demonstration scenario where we are showing that communities can pool their resources together and can coordinate with each other. You can make the use case much more intrinsic. You can make the use case with the whole feeder sort of into different communities and demarcate them. We just wanted to show a demonstrative use case out of this.
Thank you.
Sure. Yeah, again, key learnings that we got out of this from the transactive energy concepts, how consensus-based distributed coordination would work, what are the impacts of asynchronous communication, so what are the communication requirements to enable such distributed architectures or such distributed coordination. And then one ongoing effort is to identify what are the potential impacts of having wholesale markets. Basically, if some of these community markets starts increasing, it might cause a lot of variability on the distribution system operator because the operator is exporting all the power at some times of the day and no power at all at other times of the day. How would that impact on wholesale market operations and also on the DSO revenue? So that's some ongoing effort which we're investigating. This came out of Helix Plus and the PNL-WSO DGRT program in terms of some of the software skill sets used again, GridLab as a distribution system simulator and Helix as the co-simulation tool. So just wanted to sort of shift gears a little bit. We have been looking into some coordination strategies for enabling DER coordination, basically DER to grid, DER to community, community to community kind of coordination. Shifting gears a little bit, I also wanted to give you a little flavor of how transactive energy is not just effective for energy arbitraging. You can also use transactive energy during emergency conditions. So extreme events, extreme outages have been recently increasing a lot. One of the major modern day concerns of utilities is how do we deal with such events? And essentially, how do we also reduce the repercussions on the lives of society and people? So I have two figures which sort of shows a California ISO extreme event is during the heat wave. And you would see what California ISO did is they have a system through which they can send text alerts to their customers. And essentially, you being a customer to California ISO, basically to SDG or PG&E, you would get a text alert saying that we are in an emergency, can you please turn your load down? And just through text alerts, they saw that they were able to turn their loads down and were able to somehow avoid some level of load shedding or load curtailment. And on the right, I'm showing Texas freeze event. We are all aware of it. It's been one of the most devastating events that has happened in 2021. Extreme cold events, and essentially a huge amount of Texas got lost its power supply. So how can transactive energy sort of come in and help the grid during such stressed out emergency conditions? So I talked about text alerts. Another thing that utilities use are rolling blackouts. So these are blunt instruments that utilities use to just chop off feeders to turn down loads. And what essentially happens due to rolling blackouts is that only some of the feeders that have critical infrastructure, like hospitals, like important commercial buildings, they sort of stay on, whereas most of the other feeders get dropped off. But the one thing that have sort of shown that there has been a huge disparity in terms of its social impact. So even lower priority customers would have higher priority loads. For example, refrigeration, for example, water heater, even lights. So if at all possible, how can we also supply some of these lower priority customers or who having some high priority loads? Regular transactive mechanism might not be super effective because you can see that during these emergency conditions, there have been huge spikes in market prices. Like this is ERCOT price, and this is price of around $9,000 to $10,000 per megawatt hour. So if those prices gets exposed to customers, the customer would basically just not be able to pay them. So what we have come up with that, why can't we can do something like a sugar rationing or a gas rationing that has been done before? Why can't we do that as energy rationing during such emergency scenarios? That customers will be provided with a base allocation, and based on that allocation, customers can basically effectively use that. Let's say you have 1 kilowatt, and do you want to turn your lights on, or do you want to heat your water quickly? So based on that, customers can sort of decide what's their priority equipment and can turn it on and run it for a certain amount of time. So how can transactive energy be used here? Essentially, what we have done is this is a flow of the mechanism. So all the devices can communicate their requirement, relative need for energy with respect to price and quantity. A base allocation coming from utility based on the extent of the outage. On that base allocation, what we do is we sort of we distribute the demand curve into demand side and supply side. So the demand side is basically what the customer that didn't get served and wants to get out of the market. The supply side is basically what the customers could afford based on the allocation. So these are the selected set of loads that the customer could operate. So you can see that the allocations for sale are the two big blocks on the right side of the demand curve. So these are basically some of the end user equipments that the customer could operate on that base allocation. And everything else the customer cannot operate on the base allocation and is looking to see if it can buy off from the market, if some other customer is willing to trade their allocation. So there is a concept of willingness to play and willingness to accept, whether a customer would pay the same money to consume or pay the same amount of money to sell it back to the market. So what we have assumed for simplicity is that the customer's willingness to pay and willingness to accept is the same. And then essentially those demand and supply side goes to the DSO. The DSO takes into account all of the demand side curves, aggregates them, all of the allocation for sale, aggregates them. And essentially what it does, it sends back an auction price and auction quantity. So what might happen is that a customer who is willing to sell some of its allocation might give up a particular appliance that it was willing to turn on lieu of financial incentives, and someone who is willing to pay a little more might take that extra allocation and can turn on an additional equipment that they want to operate. So essentially, everyone gets a ration, and then everyone are trading portions of their ration with each other. So a very equivalent scenario is during sugar rationing. Let's say everyone gets 1 pound of sugar. And what you do see is that you don't want 1 pound of sugar. What you do is you take half a pound of sugar and then sell half a pound to another neighbor who's willing to pay a little bit more. Essentially, that's what we are trying to do out of electricity. And those basically get to dispatch devices and essentially controlling the device level controllers. So this is what we call as the transactive emergency power allocation mechanism. What we have done is we have sort of a proof of concept demo on a taxonomy feeder. What we have done is we have sort of created a DSO availability limit, which is, as you can see, that mark around 450 is what is the available power at the DSO. And then the outage kicks in for 12 hours at 19th February to the noon of 19th February. And essentially, you would see that with this allocation mechanism, from a DSO perspective, it's able to curtail its demand and maintain it consistently at that level. So it leads to a really good utilization. And on the top, that what I have is the energy not served percentage with respect to a slider setting. So the slider setting indicates how much is the customer willing to sell off their energy with respect to how much is the customer not willing to trade off its comfort for incentives. So as you can see, as the customer's slider setting increases, you would see that the customer's energy not served drops to almost zero. That means the customer sort of is paying more to other customers, essentially buying off their portions of energy and getting their energy served, whereas the customers who are willing to trade off more have some level of energy not served as well. So what essentially this does is this provides an additional revenue stream for customers to sort of sell some of their allocations to others and thereby earn money. You would see that there's the percentage change of cost on trading these allocations, where some customers would have minus 500, which means essentially they're earning profit, and some have plus 500 to 1,000, which means that they are sort of paying the money out. But the key takeaway is that transactive energy can also be used in these emergency situations to control customers and essentially use demand flexibilities that is inherently present within the customers. This is an effort that's happening through the Transactive Systems program. We are currently trying to scale this up to demonstrate how effective it would have been for ERCOT during the freeze events. So now with these mechanisms, I also wanted to talk a little bit about some of our modeling capabilities. These are basically taking some of these pilot mechanisms that we are developing and how can we make them at scale and model regional grid response grid infrastructures. And through that, how we can implement transactive systems and then quantify what is the value of transactive energy if we implement them on ERCOT level. So this is out of a DSO plus T study on ERCOT. I have just one slide for this, but this has been an effort for 3 to 4 years with a huge number of P&L staff members sort of putting a lot of time and energy into this. This essentially is the model from every end user customer level up to the whole ERCOT ISO. So we are modeling all the load zones in ERCOT, all the weather zones in ERCOT, modeling them with end user customers, populating each feeder, having multiple feeders, populating DSO, and then essentially having the wholesale market of ERCOT. And you could see that we could get representative load profiles of ERCOT for 2021. This has been done for 2016 as well. And some of these capabilities are also available online for users to use them. There is a series of reports on DSO plus T as well as our DSO plus T study website. Now, how can we use some of these modeling capabilities, right? So one of the things that we did is we took those end user load models of the entire Texas grid, and we sort of imposed 2021 extreme weathers on those. And then we could see that we could emulate the responses that ERCOT saw in 2021. So you would see the blue and the red. So the blue is basically what we were getting out of, blue is essentially what we're getting out of the GridLab simulations, out of those grid response models. And then the red is essentially what ERCOT saw. And you would see based on the forecast load projections, we are very close to predicting what actually happened in ERCOT. And how we can use this to even predict what would have happened if the temperature was even worse, or what can happen in California if you get a heat wave. Our idea is that to use these modeling capabilities to demonstrate the impact of transactive energy. For example, if something like a power allocation mechanism was in place in Texas, how would it have impacted customers? How would have it impacted in terms of saving the customers from blackouts, or how would have it impacted from customers in terms of reducing those very high scarcity prices? So we have an ongoing effort through Maple Leaf project. We're using some of the same philosophy of the bottom-up modeling approach, and we're trying to model this for ISO New England, specifically the Vermont load zone. This is in part collaboration with Velco, where we are trying to model all the distribution utilities that are connected on the Vermont load zone. There are utilities like BEC and GMP who are partnering with us, and we are in the process of sort of calibrating and tinkering these load profiles. As you can see, we're getting closer and closer towards getting our grid response models to emulate real load behaviors that has been seen by ISO New England. So there is one more work. This is sort of ongoing work in collaboration with WSU, another example of how 1 + 1 is greater than 2. This is a wholesale market emulator work that has been designed to demonstrate capabilities of how can we emulate wholesale market behavior. We have been using Matt Power most specifically to do some of these capabilities, which includes AC power flow, deterministic OPFs for single period and multi-period, which means real-time markets, and then also stochastic OPFs, where we can take into account the variability and uncertainty of renewables. So what's the impact of dispatchable demands, which is demand level flexibility on these ISOs, and also what's the impact of grid scale storage. So essentially what we did is we took Matt Power most, building up a wrapper on top of it, which essentially enables all of these functions to be very easily used. And you can just make small configurations and then run your use cases. So our goal is to sort of help users to use these tools and not having to go through the rigor of learning each and every nitty-gritty and focus on the use case and the mechanisms. So this also have several functions. So you can see there's a list of the functions here, which includes something like run day-ahead market, run real-time market, send day-ahead allocations through Helix, get day-ahead allocations from Helix, send real-time allocations via Helix, get real-time bits from Helix. So basically, we all have this. We're having this custom-made function, so you would just be able to plug and play with these functions while you're trying to develop your use cases. This code base is open source. You can hop onto GitHub and download a clone of this code base and then start implementing and playing with it. Here are some template results of that. Again, implemented it on ERCOT. You can see some of the generation profiles we got with respect to actual ERCOT. So this is the gen mix that ERCOT saw, as well as some that we generated out of this wrapper interface. You can also play with unit commitment decisions, different penetrations of demand flexibilities and impact on pricing. This is an ongoing AGI effort with Washington State and Washington State University sort of helping us develop this. This was part of the Helix project, and I think it's getting focused and shifting into the Transactive Systems program. So just a brief summary. I know I went through a lot of content, but the idea was to give you different flavors of transactive energy, how it can be used for different coordination strategies and different grid services. So what we have seen that how we can use transactive energy for prosumer to grid kind of coordination, for distributed community-based coordinations, and how we can effectively enable customers to provide these services, right? We can do peak load management, we can do emergency support, basically just figuring out the right mechanisms. I think the main work starting from here is to show impacts on large-scale implementation and essentially work with utilities in trying to figuring out the roadblocks of getting this technology to deployment. In terms of simulation support for transactive energy systems, just shown you distribution grid response models. These are regional distribution grid modeling support that PNL can provide. Feel free to reach out to us, and then we'll try to get you in touch with the right team to help you out with access to some of these response models. Wholesale market emulation, this is an ongoing effort with WSU, so every one of you would have access to this. You can use this to sort of find out what are the wholesale level impacts for a distribution level control that you are developing. And then here are some links to some key resources, which is the Transactive Energy Simulation platform, which can be a good starting point if you're interested in learning more about transactive energy. And then the Matt Power wrapper, which is the wholesale market emulator. So with that, I think that's all I've got. So we're really open to questions and discussions.
Okay. We have a lot of people online, so.
I can start.
Yeah, go ahead.
I want to hold the conversation, but I always have a question about this. Whenever we talk about transactive exchange, right? How do you make sure, because energy flows on the wire, right? How do you make sure that the billing and all takes this into account that I am sharing my energy with a specific consumer? Because power will flow, whatever is the lowest path route, right? How do you make sure that? Or at least how is the billing incorporated in these problems?
Yes, I think that's very important. Probably as we go through different architectures, right? So, as if you are looking into those bottom-up hierarchical architecture, so I think metering is really essential. So if we have meters on every PCC of every stakeholder, so for example, customers, distribution system operator, and transmission operator are all stakeholders. If we have meterings at each one of those PCCs, a metering at the top of the customer, a metering at the top of the DSO, and then ISO sort of has very intense level metering, right? So essentially, if we can take into account those meterings, we would know at every time step how much energy has flown through that meter, and be it positive or negative, that sort of becomes the base metric on top of which we determine cash flows. Basically, this is the amount of energy that has flowed in, this was your commitment, your difference is going to be paid by real-time price, your commitment is going to be paid by day-ahead prices.
Right, but let's say I'm sharing my energy with my neighbor, right?
Yes.
So let's go a step further from there. So we are, I understand that, based on the consumption at my local meter, I can be charged, right? And if net metering can help me charge whatever I'm consuming and whatever I'm actually not consuming from the allocated resource and whatever is the additional benefit out of that. But in the transactive setup, let's say I decide that I want to sell to consumer A versus consumer B, because consumer A says that I'm giving you 10 cents more, 2 cents more than consumer B, right?
Right.
But the flow through my meter is the same amount, right? So how does that meter get into, is there some sort of contraction mechanism that goes, which is not really the energy flow, but more of a money flow that's going on? Or?
Yes. So this is something that more or less shows up in the peer-to-peer architectures or in the community kind of architectures. And and this is more on the research stage, right? No one has sort of tried to do an actual peer-to-peer market in operation. So most of the time, what they do is they keep the ledger and the flows separate. So the flows are sort of measured on the net metering scale, and then the ledger is what just happened in the transaction, right? So on the money side, you can keep track of which customer has bid which price, which customer is willing to pay that price, and essentially the energy would balance out at some level of PCC or some level of interconnection. The energy would balance out, but it's very tricky to do those. Is that the particular electron that went from that house's end to the same electron flowing into the other houses buying it, right? So that tracking is really difficult, and that's one of the main bottlenecks of some of these peer-to-peer architectures.
Because to me, it seems like that it's just playing on information asymmetry,
Yes.
right? That's all that's going on. And
Exactly.
real amount that's flowing is irrelevant.
Yes.
Have you seen any work that tries to find out, let's say, some sort of resolution to this question, that this is what the actual market will settle to, which is more rational from the perspective of both the physics as well as money?
Right. And the answer to your question is I have not seen any work focusing in this tracing electron flow problem, right? Most of the reason why these peer-to-peer markets are good in research but not good on paper is basically just because of this question. It's very difficult to keep track of those particular level of energies that are flowing in and out, and it becomes so distributed that regulation has to play a big role in trying to enable them, right? The consumer-centric architectures are a little more evolving because there your number of points become less. So you're pooling 20 customers together to one point, and if you have a meter on top, you essentially can try to make them work. Right. And if your communities are sort of geographically aligned, then it's easy to track the electron flow. So that's a really interesting point. I have been thinking about this too, and there is probably not too much of
let's check something out. How do we get to the chat?
Yeah, there is no new chat. It should show up as a message.
Yeah.
So there's no
new
chat. Okay, so we'll ask the people online to put it on chat. Then we can handle that.
So Manish,
let's
privacy will be an issue, isn't
Yes,
it? Because how much of these community transactions they are willing to share with the DSO, but then you have to know in order to reconcile the meters with the ledgers, like you were saying.
Yes.
So that's going to be another layer of complexity.
Yeah, and privacy is a real challenge. So there are sort of like blockchain technologies evolving, trying to take into account some of these privacy concerns. What the price responsiveness does, it gives away a little bit of the privacy information, but it's still, since it's a aggregated curve of all the devices, someone who really wants to hack into what the appliances of consumers are incorporated to that curve, they have to do some non-intrusive modeling. So that decreases the complexity of the privacy issue. So one aggregated bit curve sort of takes the privacy concern a little bit checked, but still it's very much evident that privacy is going to become a problem as consumers don't want to expose out their thermal preference. They don't want to expose out their price responsiveness.
But other than the privacy, the reconciliation process is not going to be that different from the reconciliation process today. See, every market has to have a reconciliation
This
process
is at micro
afterwards.
level.
What?
This is at
You just need more data. So you'll have to process, if you only have 20 players playing in the market today, then you have to reconcile between the 20 players. If you have 2,000 players, then you'll have to reconcile between 2,000, but the math is the same.
Yes. And we have done some studies. I think we had a big valuation team that sort of looks into cash flows. So essentially, how would this transactive energy eventually trickle down to DSO level revenue, trickle down to customer level revenue? And there have been some really interesting results that we have come up with, that how transactive can help take the tariffs down, how you can come up with the rate structures. And essentially that is just with this simple architecture, basically this top-down or bottom-up architectures, this is still that complicated. If we get to those micro levels of peer-to-peer interactions, taking into account cash flows will be extremely complicated.
And then the question arises, is it worth doing all that math for few pennies?
Right, exactly.
Yeah, just a follow-up question here. So I think the other concept you presented that was really interesting, like the energy rationing.
Yes.
So, I mean, I can realize the way the market works, and we can realize even the privacy through the blockchain and other things, so ledger flows. But I still working around like how the physics, like what Anamika pointed out correctly. So how exactly that rationing works, because especially you already cut it down to the lower amount that was already allocated, then how do you ensure, even like I have a 5 kilowatt of hour energy consumption, how do I make sure like I'm only cutting down to 1 kilowatt hour? I don't have a unreliable infrastructure so far now, but
yes.
So what exactly the challenges?
Yeah, I think that's a really interesting question. I'll go back to that slide on rationing. Let's see. Yeah, so essentially, some of the base assumption that we have over here is we have those very intelligent appliance level home energy management system hooked onto your circuit breaker. So what they can do is they can find out individual sections of your circuit. So this particular part is basically representing your ovens, and your this particular part is representing your heater, HVAC, and some plug loads. So what we have done is we have sort of taken and broken down. This is our plug loads, this is our communication loads, this is our heating load, cooling load, water heater load, and what we do is we come up with those base. So our base assumption is that intelligence or that amount of device support is available. And if that's available, you can come up with that breakdown of individual appliance level load. So those 5-6 blocks that you are seeing on the curve, price quantity curve on the top left. So individual blocks are individual appliances. And now since you have an estimate of how much quantity you're going to consume on the plug load, how much quantity your refrigerator consumes, how much quantity your water heater consumes, you can ensure through an agent that if your allocation exceeds over, let's say you can only consume your refrigerator and your lights and nothing else. So what the transactive mechanism does, it sort of steps in and says that all the other 3 circuit breakers are off, only this circuit breaker is on. And that's how we are sort of ensuring that you can maintain customer level operation at a very precise level and precise breakdown of individual loads.
Yeah, that's really interesting. I mean, I'm still see the control aspects and the market-wise, I'm pretty much clear, and I assume that home area network is still available, but the control-wise,
yes,
you enable the control from the customer level to the aggregator, then
right,
to the DSO, then only those are the issues I see.
Yeah, and I think the main sort of technology to market piece is that control. Is that control of intricate pieces of your circuit breaker, right? If you intricate piece of your circuit panel and you can trip off one piece of the circuit at a time, and there are companies that are coming up with this solution. So these are I think one of our collaborators, Trevor, who was sort of spearheading this effort, he came up with some companies, and they were sort of just selling out these equipments who were basically advanced load control, and these are just this equipment that would hook up to your panel and would give you this precise level of individual breaker level controls. So these are coming up, and essentially you have to find out a cost for the customer, right? That if the customer is spending $400 to buy this device and mount it on its circuit breaker, is it worth it for the customer? Or if a utility is spending that amount and mounting it on the customer, is it worth it for the utility? So you have to probably go back, do some of these large-scale analysis to find out the true business case and who is going to be the enabler for these technologies.
Yeah, the last one is what is the role of the utility in terms of the transactive energy? Whether they get the benefits or not, because ultimately every customer, no matter whether community or the customer, they're going essentially using the infrastructure there.
Yes.
And they put a lot of investment in that.
Absolutely.
So what is that? Because anyway, you're trading between the communities and the consumers. So do you have a mechanism to pay off the utilities, or how they get benefited? How do they ensure that the reliability of infrastructure is still in place or intact?
Right. And that's one of the key questions, right? So during emergencies, the cases are a little different because during emergencies, you would see the price spikes happening really high. So if you are buying electricity at $10,000 per megawatt hour, if you save 1 megawatt hour, every hour you're saving $10,000 as a utility, right? So that there is a huge cash return during emergencies, but during day-to-day operation, it might not be the case that the cash return is huge, but there are also utilities value flows are not just in the arbitrage, but also on infrastructure deferrals, right? So they might be able to push out a substation upgrade. They might be able to push out a transformer or service transformer upgrade just by tapping into these demand flexibilities and using them to control their load growth. So there is some valuation work which we are doing. I don't have it on my slides, but I can link you up where they are sort of taking into account these arbitrage cash flows, these infrastructure deferral costs, and also investment. For example, AMI is an investment from utility, right? And you need AMI support to sort of enable some of these technologies. What's the balance sheet for them? What's the cash flow happening in between utilities and customers? So there are some numbers which we have populated out of the DSO plus T study for the whole of ERCOT. And I'll provide you the link to that valuation report, and you can see some of those equations through which we are calculating these annualized numbers.
So maybe one way would be to just tax the transactions and
Yes.
and pay off the utility.
Right, like utility becoming an operator who maintains the transaction platform.
I want to see if there's more questions from the students.
I have a question.
Yeah.
So you mentioned that tracking the electron flow is a bottleneck, but I cannot think why would that be important? Why would we want to track electron instead of just how much energy is flowing?
So basically, if you as a customer are trying to sell electricity, for example, you from, let's say this campus is trying to sell electricity to somewhere in Walmart, near where Walmart is located, right? And then you said that you are going to sell the electricity at some price, and then someone at Walmart is going to buy that electricity at some other price, right? How do you ensure that it's your energy that's being sold and being bought by the Walmart agency, right? So to track those exact electron flows, that's the tricky part. What you can do is calculate at some upstream level, what's the net flow. And if everything balances out, and if you have a very accurate representation of your flexibility, you can say that we assume that WSU has given power to Walmart, or Walmart has given back to WSU.
I think what you do is, again, go back to how it's reconciled today. See, you cannot track electrons anyways, right? So if say A has said that they're going to sell B 50 megawatts, and then it varies all over the map, but you can check how much A has generated and how much B has, and you do it on the net, all right? The problem arises now if you have not just A and B, but you have A, B, C, D, E, F, G, then you have to reconcile which ones, but you work on the nets of each of these on time, okay? So at this time, and every 5 seconds, or something like every 2 minutes, you update that reconciliation. So that's the only way you can do it. Sorry, I think.
Bookkeeping, yeah.
Thank you.
I think Hayden left a comment that, yeah, utilities will essentially become platform operators to enable some of these transactions.
Yeah.
So,
Yes.
so what are some of the challenges you faced while doing system level simulation?
Oh, the challenges are numerous. So I think one of the main problems is that you're doing everything through empirical models. So you're starting from a very prototypical or taxonomy feeder, which is representative of that particular location. You're populating it with regional level characteristics. So residential customers, thermal envelope, their load distribution, their fuel type. So you're using some of this distribution or statistical data that the government collects. So basically EIA sort of has this collection through residential surveys and commercial surveys. And through that, we are populating our backbone infrastructure with house models of residential customers and then commercial customers. And then what we have to do is eventually scale it up to try to tune and see how close we can get to actual regional level response models, right? So there is a huge number of challenge in terms of tuning and trying to find out the right mix, because the statistical data is really sparse and you're trying to use that data to predict a very accurate response. So there is that challenge. Again, complexities comes once you try to replicate the wholesale side. On the wholesale side, again, there's not a lot of information. You're trying to use some models, some empirical data to predict generation prices, to predict actual LMPs on the system. So I think that's one of the key areas which we found out that predicting the actual prices is very difficult, because we don't have those model availabilities. We don't have those price curves for every generator. And then eventually making everything work, right? Making this model from end user customer to feeder, having multiple feeders to DSO, having multiple DSOs talk to an ISO, and maintain this whole co-simulation infrastructure. Just to like solve this problem, you would basically put it on a run and get results back after a week. And then you would go and see, okay, something went wrong, you go and retune it, and you would keep doing it. So there's a lot of turnaround time. So we do it normally on an HPC infrastructure. We sort of set different nodes and run DSOs on different nodes and then exchange information. So these are sort of the challenges of large scale modeling, which is you probably have the theory really right, but it requires some implementational tuning, which you can only understand once you are starting to build up the big large scale simulation.
But are we talking about two different things here? You're talking about simulating what will happen,
Right.
which is very complex,
Yes.
right? But suppose you have a market system, transactive system or whatever set up. The other question is, will it work on the real system?
Yes.
Okay, and this is what you're trying to answer with this.
Yes.
But once you think it can be done, the actual implementation of this is much simpler. You don't have to worry about the
Exactly.
models. Of the
validation.
Yeah.
Yeah. I mean, the actual implementation sort of gets into the regulatory zone, right? Where we sort of feel like that's not our territory, where we want to say that this is how it's
Somebody else has to
Somebody else.
fix it.
Exactly.
Go ahead.
Yes.
Talking about these transactive markets, I think I've seen like a similar model where a retail market is actually selling energy to the customer, and you actually have the opportunity to select the percentage of renewable energy in your system, right? I think it's airport or pigeon, I can't remember, but does this have anything to do with this transactive market too?
Yeah, because transactive, we are just showing you some flavors of transactive. What we essentially want to say that transactive energy is like enabling customers to express their flexibilities, and incentives is like a value. So you would just get incentives, and that would help you drive your controls, drive your devices as a value. So for the kind of transactions you're talking about, where a percentage of the renewables they can bid into the market, that's essentially very similar to this kind of flow, where you're using your DERs, using your DER flexibility and trying to help them participate in providing grid services. And that's sort of the base foundation of transactive energy.
Well, I'll take one more question. Yeah. Go ahead.
So what is the common practice for accommodating network losses into the transactions?
Right. So I think what the common practices is, since this prosumer to grid model where customers are trying to participate in wholesale markets, that's still in the works, right? After PERC order came out, everyone is trying to find out what's the best way to get these aggregators, and then aggregators participating in wholesale markets. So the losses sort of get into account through the distribution network operator. I mean, the operator sort of calculates its own losses and then includes that in their demand forecast, or includes that in their short-term demand that they're raising in the real-time market. And that's how they get reflected on the wholesale and they get valued for. And eventually during revenue breakdowns, you are doing metering at the DSO level. So the losses are getting incorporated in that DSO level. On the transmission side, the losses are being calculated through OPMs, right? But on the distribution side, in practice, the losses are not dynamically calculated. They're mostly sort of empirical, or they're mostly incorporated through value flows. Although in research, we do try to incorporate power flows. We do try to incorporate power flow equations and then try to estimate the losses, because they might start getting interesting with more DERs. But with the state of art, the losses are not calculated with that precision. They're probably just estimates that the DSO does.
Okay, thank you. I think we'll stop here because otherwise the pizza will get cold, and because we can already smell it, right? And thank you for there's no pizza for the online people, so sorry about that, but thank you for joining us in any case. Yeah, thank you.
Thank you.